Hello. In the previous video on distribution functions, we have defined the distribution function by the relation n of e is equal to g of e into f of e, where n of e denotes the number of particles having specific energy E, g of e denotes the number of states with energy E, and f of e denotes the distribution function. From this relation, we have rewritten f of e for any particle family as equal to n of e by g of e. So from this we have seen that the distribution function denotes the average number of particles per state having an energy E at a thermal equilibrium at a temperature T, or it denotes the probability of occupy a state of energy E at any temperature T. Now, as we have seen that the distribution function is different for different family of particles, we will see what is the form of the distribution function for the three particle families involved. As the syllabus do not demand the derivation of these equations, we will have to memorize this equation by just making some comparisons for the time being. So the Maxwell-Boltzmann distribution function, which is applicable for classical particles, like molecules of a gas at a low density and all, is denoted by f of e. To denote that this is the distribution function for Maxwell-Boltzmann, we are writing a subscript mb, f mb of e. That's the way in which it can be represented. That can be written in several ways. I'll be writing in different ways. You can memorize one of the equation which is which you feel easy. So the Arthur Baser present edition textbook defines this one as e raised to a into a is some constant, a e raised to minus e by k t, a e raised to minus e by kt. That is a way in which the present edition of Arthur Baser reports the Boltzmann, Maxwell-Boltzmann's distribution function, which can be converted into several other forms. So let me introduce the quantities here, where E is the energy of the level. Okay. See, K is Kb, the Boltzmann constant, whose value 1.38 × 10⁻⁻23 joule per Kelvin, and T is the absolute temperature, means the temperature in Kelvin, and A is something some sort of a constant, like a normalization constant, whose value will depend upon the nature of the particles of the system. Maybe also it can be a function of temperature also. And another way of writing this equation is just writing equal to a into e raised to minus beta e, a raised to minus beta e, where you can see what is this beta. Beta e is replacing 1 by kt. So see that beta is equal to, in all these distribution functions, wherever we use beta, remember beta is representing some sort of an inverse temperature, okay, multiplied with, of course, the Boltzmann's constant. So beta is equal to 1 by kt. That is the thing. So a e raised to minus beta e, and the same function can be expressed in yet another way. That is, it's also written as 1 by e raised to alpha into e raised to beta e. This is yet another way of writing it. E raised to alpha into e raised to beta e, where this new quantity alpha is equal to minus mu by kt. Minus mu by kt. You will see that there are new terms that is hidden that comes out. Okay, that is one reason why you are not insisted on for the derivation of this equation, because that is quite lengthy. You need to have some other theoretical support. Of course, you will be deriving it in your postgraduate classes like your seniors are doing. So where alpha is a constant and this mu, I had already introduced this mu in some of the previous lectures. This mu is what is known as the chemical potential of the system. That is yet another intrinsic property of the system, chemical potential, like pressure and volume. Chemical potential of the system, and that is responsible for what is known as the chemical equilibrium. We have defined thermodynamic equilibrium as a combination of mechanical, chemical and thermal equilibrium. For mechanical equilibrium, pressure should be equal. For thermal equilibrium, temperature should be equal. Similarly, for chemical equilibrium, this chemical potential should be equal. Okay, so that is alpha equal to minus mu by kt and beta equal to 1 by kt. And these two constants, beta and alpha, which are functions of temperature, you can see beta depends on temperature and alpha is also depending on temperature. Inversely, this alpha and beta are usually known as Lagrangian multipliers or Lagrange's multipliers, Lagrange's undetermined multipliers. That is the term, okay, in thermodynamics. Just this is only for your knowledge I am mentioning. Don't worry about all these things. Your task is to memorize one of these equations that I am giving for each of the distribution function. Okay, so then your job is done, and try to have some intuitive idea regarding what these functions are denoting. Okay, don't worry much about this one because it's beyond the scope of the present syllabus to explain everything. That's I told you, this is separate paper. You will be able to do it, okay, when time comes. Okay, so f of mb, either you write a e raised to minus e by kt or a e raised to minus beta e. This is one and the same because this minus 1 by kt this 1 by kt is represented by beta. Okay, and another thing, okay, is this can be equivalently written as, I prefer this one, okay, because that is more memorable one. So e raised to alpha and e raised to beta e. Can you combine this exponential? So you can write this one as e raised to alpha plus beta e. 1 by e raised to alpha plus beta e. And this is what I prefer you to use. Okay, or it's all up to you. You can just, so f of mb, which is a function of e, this is equal to 1 by e raised to alpha plus beta e. So you can see that on the right side there is a e here. Okay, that is why it is written this f is a function of e. F is a function of e because the equation depends on e, and alpha depends on the properties of the system. Also, it's a function of temperature. That is why all those things are shown here. A. So this a also involves what do you say? You can say a here is equal to something like 1 by alpha or something like that. You can just identify. So that is a Bose distribution function. Maxwell-Boltzmann distribution function. Similarly, you see the Bose-Einstein distribution function can be derived, and it finally turns out to be f Bose-Einstein, which is also a function of the particular energy. Okay, that is given by another equation. This can be written as 1 by, this is the way in which it is written. Either you can write it as 1 by e raised to alpha into e raised to e by kt, e raised to alpha into e raised to e by kt. Don't worry about these expressions, just see that finally I will tell you that these are all same. Minus 1, e raised to alpha and e raised to e by kt minus 1. Can't you rewrite this one in another form? That is 1 divided by 1 divided by 1 by kt is beta. This is not 1 by kt is beta. So this e by kt can be written as what? Beta into e. So it will be 1 by e raised to alpha, that's why I told you that these are all easy, okay, e raised to alpha into e raised to beta e is not the same thing, minus 1, or simply combining, we'll reach a very simple expression, that is 1 by e raised to alpha plus beta e minus 1, which I suggest you to memorize. And similarly, the Fermi-Dirac distribution function is given by, remember we are not deriving these equations can be derived by some lengthy steps, okay, using Lagrange's undetermined multiplier technique. So this is f for Fermi-Dirac, distribution function for Fermi-Dirac, that is given by f of e is equal to, the same manner you can write. What will be the thing? I think I'm just writing it. After that you can just see the similarities. E raised to alpha into e raised to e by kt. This is the way in which you will see in your Arthur-Basel present edition. Instead of minus 1 above, here it will be plus 1. That's all. No difference at all. So 1 divided by, same thing can be written as e raised to alpha into e raised to beta e plus 1, or finally it can be written as 1 divided by e raised to alpha plus beta e then plus 1. So this the final equation I want you to memorize. Now you look at the three distribution functions, f of mb, f of be, and f of ft. F of mb is applicable for classical particles. F of b is applicable for bosons. This is applicable for bosons, and this function can be applicable for any fermionic system like electron, proton, neutron, etc. for fermions. And there is quite a similarity between the final equations. So you look at this equation, it is 1 by e raised to alpha plus beta e, nothing else. This is 1 by e raised to alpha plus beta e minus 1, and this is 1 by e raised to alpha plus beta e plus 1. So the difference is, you can write it like this. In general it will be something like, in general I can say, okay, so I'm generalizing it here, somewhere here, f of e is equal to, this is the easiest way to remember, 1 by e raised to alpha plus beta e plus or minus some a. I suggest this is the way in which you can remember, where when a is equal to 0, you will get this expression, a equal to 0, it gives you what? Maxwell-Boltzmann. When a is equal to, okay, when a is equal to, just you can see, yeah, plus or minus 1, plus 1, okay, a equal to plus 1, better plus a you write, no, is it right? Plus or minus you can avoid, this minus you avoid, here you take it as just plus. A equal to plus 1, you get what? The Fermi-Dirac. And when a is equal to minus 1, you get what? BoseEinstein. Okay, BoseEinstein. Now for the same value of one thing, okay, so this plus 1 minus 1 makes the difference. For the same value of this e raised to alpha plus beta e, suppose, means for same value of temperature, same value of energies, if you are making a comparison between the three distribution functions, okay, if you make a comparison between the three distribution function, that is shown on the right side. On the right side, the graph shows a comparison distribution function. Here on the x-axis, I am taking energy. Suppose energy in units of temperature, kBT. That also you can write energy in units of kBT. Okay, or it can be E by kBT also, whatever, depending on the scale. And on the y-axis, we are taking f of e. The distribution function is taken along y-axis. Okay, and on the x-axis, we have taken the energy. Then you will see the variation of the distribution function is shown by the three graphs here. The red graph shows BoseEinstein distribution function variation. The blue curve shows the Maxwell-Boltzmann distribution function variation, and The green one denotes the Fermi-Dirac distribution variation. And you can see that all these three distribution functions are coinciding when energy is high. So at the high temperature limit, or the high energy limit, not the high temperature limit, at the high energy limit, we can see the two quantum distribution functions, namely Bose-Einstein function and the Fermi-Dirac function, are merging with or are coinciding with the Maxwell-Boltzmann. This is the classical distribution. This is classical, this is quantum, and this is also quantum. So all the three distribution functions are coinciding, okay, in the high energy limit. That is one feature on comparison of the distribution functions. Another thing is that you can see that here you see the value of the distribution function is 1, right? Here the value is on the yx 1, okay, and you can see that this is a rough sketch only. The value of the Fermi-Dirac distribution function will be always less than 1. I will tell you why in the next video. You can see the value of the distribution function, Fermi-Dirac distribution function, has remained less than 1. That is what you have to note. It's always less than 1. Okay, the graph never goes above 1. Whereas you can see which one will be having greater. Okay, you can see that the Maxwell-Boltzmann distribution function, see the Maxwell-Boltzmann distribution function, as you can see here, if you leave alone this A, you can see that there is an exponential decreasing function with the E. Exponentially decreasing function with the energy. That is why you can see there is an exponential decrease that is shown with the energy E. There is an exponential decrease. Okay, and when you compare the three distribution functions for the same value of E, you can see that, for example, you take the same value of E. See, for the same value of E, you take the value of Fermi-Dirac, you take the value of Maxwell-Boltzmann, and you take the value of what? Bose-Einstein. You will see that the Bose-Einstein distribution function will be having greater value, followed by the Maxwell-Boltzmann, and the least will be for what? Fermi-Dirac. You can understand this one if you compare the final equation of all the three distribution functions. You can see the Maxwell-Boltzmann distribution function is 1 by e raised to alpha plus beta e. You call this one something like x. This thing as x. So this one is equal to 1 by x. Okay, this one is 1 by x minus 1. And this one is what? 1 by that x plus 1. Can't you see which one will be giving you greater value? So you can see that 1 by x minus 1 will be having greater value, followed by 1 by x, and minimum will be what? 1 by x plus 1. That is the significance of this plus 1 and minus 1. Okay? Oh, got it? Is it not? Because x minus 1 in the denominator, some x, where x is equal to e raised to alpha plus beta e, I am calling it, okay, for the same value of that. So x minus 1 will be what? X minus 1 will be greater than, okay, this 1 by x. 1 by x minus 1 will be greater than this 1 by x, which will be what? Greater than what? 1 by x plus 1. So that is why the functions are having this type of nature. So see that the similar, almost a similar graph is given in your textbook Arthur Baser for the comparison of distribution functions. If it is needed, see that you memorize that graph, try to understand the graph. The values need not be memorized. At least the variation is okay, the nature of the variation and the feature that they are merging at high energies should be kept in your mind. Okay, and I would conclude this session by just showing you a tabular representation of the three distribution function, which shows the comparison. And this is the tabular distribution. This distribution table I have taken from Arthur Baser textbook itself, and I have given it along with the short note which I have already uploaded in your Google Classroom. So you can see this summarizes all the three distribution functions. First one is Maxwell-Boltzmann, second one is Bose-Einstein, and the other one is Fermi-Dirac. So you can see here the particular features are given. It applies to the system of identical distinguishable particles, identical but indistinguishable particles that do not obey exclusion principle, identical but indistinguishable particles that that obey exclusion principle. So these two are the quantum statistics, quantum distribution functions. Category particle classical. This is the boson, which is quantum. This is fermion, which is also quantum. Properties. Okay, you know already, we are examples have been given. Just distribution function, see the distribution function, the final equation that I have introduced, the last thing has been written here, and the properties: no limit to the number of particles per state. Any number of particles can get into any state. No limit to the number of particles per state because there is no exclusion principle there. Okay, but never more than one particle per state. This is the result of the Pauli exclusion principle. No more than one particle per state. Okay, so that is due to the the constraint that they should obey Pauli's exclusion principle. And you can see both these distributions approaches the Boltzmann distribution. Both the distributions approach the Boltzmann distribution at high energies, as you have seen from the previous graph. Okay, so that is a comparison of the three distribution functions. You may use this table for comparing either the distribution functions or the statistics or the three families of particles. So accordingly you modify the table as per the need, okay, that you have. Okay, so I think I can conclude it here. And one thing is left from this topic, that is a definition of or an understanding of the concept of Fermi energy. I will do that in the next day. Thank you.